molar mass and the mass of iron, which you have it here, to get the molarity, which I call it here molarity what? Molarity 1, which is the number of moles of iron. Sorry, it's slow because I'm using my finger to write, and it's kind of like hard a little bit. So number of moles of what? Number of moles of iron over what? Over volume in what? Volume in liters, of which you know the total capacity when you dilute it with DI, what I did, you had it on exactly 1 liter. You can find that. And that is why I had labeled those as M1, M2, M3. We need to label this. Right here, I'll call this concentrated solution. Let's call this concentrated conc solution. And then you took either period A or period B to make what we call working what? There is what we call working solution. Working, let us say working solution using your period A or period B. Remember in experiment number 2, you had to calibrate 2 periods, right? Using period A or period B, you fill all the way, assuming there was no air trapped, starting from 0, 0 here. If you add 0.0, 0, and then you drain or deliver exactly 50 what? 50 ml of what? 50 ml of the concentrated solution. This is 50 what? 50 ml, which went into what? What was the capacity of the volumetric flask you had here?
250 milliliters.
Yeah. This was 250 ml. This was 250, the smaller one, right? So with this is the 250 ml beaker, no, flask, volumetric flask. And let me just look for my charger. It's going to fail me, but we're okay. Just right here. So this is what we call working solution, which was diluted to 250 using a powder solution, acetic acid acetate powder solution. You prepare that. Remember that, right? So here you have your working solution, which you need to find the concentration of this solution using dilution law. M1 V1 equals to M2. All right. This is M2 V what? V2. You know this equation, right?
Yeah.
This is what? And this is the molarity 1. You had it from here. You see this? V1 here is your 50 you see here. Because you took the concentrated, the delivered 250 to this solution. And this is what you are what? What you are looking for. This is the question mark right here. And V2, what do you expect V2 to be?
250.
Yes, it is 250 right there. So what you want to say is,
so V1 would be 50 and not 1,000, right?
No, it's not 1,000. You didn't use the entire 1,000 ml here. You use only 50. Because you cannot use 1,000 ml and then deliver it into 50 ml. No, it's not going to work. So M what? M2, which is what we are looking for, is equals to, as you said, M1, right? Which you know now, time is what? 50. Because you use what? You use 50 ml of the solution here.
Mm-hmm.
Over V2.
Over
What is
250.
V2? Huh? 250, right?
Mm-hmm.
And this is molarity. This is ml and ml here. ml and ml here. So it's going to give you ml and ml will cancel out here, and you have yourself M2. You see how you end up with that, right?
Mm-hmm.
So you have your what? You have your M2. Molarity what? Molarity 2. Now, there is M1. I don't know if it's going to push out. Yeah, it's going to push its work. And then I go here. This is now, at this point, you should have your M2 sorted out, correct?
Mm-hmm.
Now, in order to generate a calibration curve, you had to deliver a different volume of the working solution into 100 ml volumetric flask. So calibration curve, you had to do what? Let's see if it's going to work here. If I put right here. All right. So I'm assuming you use 10, 20, 30, 40, 50 ml of these to collect the data. I'm skipping the part on how to prepare the standard, to determine the analytical wavelength, which I know you got that, you had no problem. How to prepare the reference solution. I want just to pick up from the observance values and the volume you use to collect the observance values. So for your case, let me ask you this. When you deliver different volume, let's say here for sample one. Sample one, what was the volume?
It was exactly 10.
10, okay. Sample two?
Sample 2 is 20.
20 ml, right? So here
Yep.
Is sample two. 3, 30,
3
right?
was 30, yeah, and then 4 was 40, and then 5 was 50.
Here is 40, and this is ml, right? This is ml right here. What was the observance of each one of them?
It was 0.247.
Hold on, let me just do the complete sample 5 here. Here, what did you have right here? This is 50 ml.
mLs. Yeah.
This is 50 ml, okay. So let's start up at the top right here. What was the observance for?
It was 0.247.
0.247, all right. This is APS, right? No, AP observance. And then the second one here is what?
0.489.
Oh no, 0.489. Is this 0.2 or 0.02?
0.2.
All right, 0.2. That's what I wanted to say. 0.2. And then this one is 0.489. 489. And then the other one is what?
0.735.
0.735. And then this one was what?
0.978.
978. And then this one is what?
1.222.
1.222, right?
Mm-hmm.
These are APS, right here is APS for observance, all right, so that you know what they are. These are observance what? Observance values.
Mm-hmm.
From Peirce law now, this is where Peirce law comes in, and from Peirce law, A observance equals to molar absorptivity. I don't have the special characters here. Let me just use E times some use length, which is the length of the cuvette, times what times concentration. Times concentration. Now, from these observance values, you see these observance values right here?
Mm-hmm.
We need to plot a curve in order to generate a curve, this one right here, calibration curve. You'll have to have concentration of your solution in 100 ml volumetric flask. Remember, these solutions right here are from 100 ml volumetric flask, right?
Yeah.
Remember what you had is you delivered from the pureed different volume you see here into 100 volumetric flask here, different volume. You had to develop the color for 5 minutes and then you collect the observance values to get these values right here, correct?
Mm-hmm.
So we need to have M3. Remember already we have M2 here, right? M3 is the concentration of the iron 2 complex, which was observing light at your specific analytical wavelength. This is iron 3. This was a complex right here of iron 2, Fe.
If you're writing it right now, I can't see it on the screen.
You can see on the screen?
No, I think you're writing it too low.
Oh, let me push it back. Like this. Can you see now?
No. I can see everything else you wrote. I just can't see that.
You can see what I'm writing right now. Let me see. Can you see? Let me see. Can you see this when I write like this? I see you. You are moving.
Oh,
Please.
yes. Yes. Huh? Okay. I just moved the screen. I can see it now.
Yeah, probably maybe it's on your end. You can see now, right?
Mm-hmm. Yeah, I can see now.
So this is what I was telling you that you need to find the molarity. I didn't want to do that. I need to we need to find the molarity of this was the complex which was observing light at a specific wavelength. We call this M3, of which we need to find this M3. Since you know observance values on y-axis, what we'll go on y-axis here are the observance what? Values you see here.
Mm-hmm.
But the challenge is how to get M3. We use the dilution law that M2, by this time, you know M2 from the previous calculation, right?
Mm-hmm.
V2 equals to M3 V3. Let's see what we know here and what we don't. Do we know M2?
Yes.
Okay, if I use a check mark, we know that. Do we know V2?
Yes.
What are the V2s?
V2 is how much you
Yeah, which is where you can
dispense
you see
into
my
the
arrow?
yeah.
You get it from there, right? Remember, we will be doing for each sample so that you have 3 values. You see, you have 5 observance values. So you need to have 3 M3s, which will vary. V2 will vary from, as you say. And this is the question mark now we are looking for, which will go on the x-axis right here. This will go right there. Can you see the arrow? And what was the V3 right here?
100 mLs.
Yeah, all of them were diluted to what? To 100 ml. Therefore, M3, you see, right? Equals to M2, which you know from the previous section, M2 V2, which is now going to change from sample to sample, all over what? All over V3, which is 100 ml. You get it?
Yeah, that makes sense.
So now, I don't know how your values will look like. You have your own values for, for M1. You have to go back and do that. And then you'll get a different value for M2. And then your M3, which you will now put it on x-axis. And you know how to use Excel to include the trend line and the R-square value, right?
Yeah.
So you should have a graph like this with the trend line Y equals to equals to M X plus or minus, I don't know what's going to be for your case, B, all right, which is the y-intercept, and include the R-square value. You know how to include trend line, right?
Yeah.
You will use this equation to analyze or determine the mass percent of iron in your unknown, which is the next thing I'm going to show you. So far, you should be able to include trend line equation of the, straight line. And M stands for the slope, which is the molar absorptivity constant for iron. This is the slope, which is the molar absorptivity value for what? For iron. And the literature value, or a good value, should be in the neighborhood of 11,200. All right. Just to give you, if you have 9,000, you have to include your graph on the lab notebook. You will tape it on your lab notebook. So there's no way you can change and just, let's say, let me use 11,000, what the literature say. You have to use your what? Your experimental value. If it is 11,000, 12,000, whatever the value you have, 11,400, that's fine. We will need this value to do what? In determining the mass percent of your sample. To this point, you understand now how to generate the calibration curve, right? And here, I'll have the title, of course, label. The title here will be observance, and then you include of, I think, iron, check the formula for that. You write it. Basically, you should have the title. This should be P, like that. Check the title so that you have the title of your graph. Okay. So that is the part A. Now, for part B, you have to pick values which you know, let's say you are unknown, analysis of unknown. We don't know. We may come back to that. Before I do that, do you have any question?
No, that pretty much sums it up for me.
Are you comfortable with the unknown? But I'll just walk you through still unknown how to do the unknown.
Okay.
So here, all right, we have calibration curve, we have everything. So what you need to know in unknown is we don't know how much iron we have in our, and that's the main objective. That was the main objective for this experiment, is to determine the mass percent of iron in your unknown. So there is no way you will know M1 straight. At the outset, this is what I'm gonna start with, that you prepared, you masked out the stated amount of unknown sample in your 1000 ml volumetric flask. What was the range? What was the volume, or what was the mass you had to mask out?
Let me check.
Check. What was the mass of your sample?
It was 0.0949.
So it was 0.
0949.
0.49, right?
0.0949.
0.49, like that, right?
Mm-hmm.
Yeah. This is the mass you dissolve, you develop, you have it. There's no way you can calculate M1 in this case. We don't know what it is, right?
Mm-hmm.
And here is what? This is 1 liter volumetric flask. And then this is right here. This is the concentrated solution, concentrated. Can you see what I'm writing?
Mm-hmm.
Concentrated what? Solution. SLN. Now, to prepare, we cannot calculate M1 in this case. To prepare working solution, you have your concentrated solution. We have here working, what we call working solution, right? Using either period A or B, you delivered, or to start off with, you had to deliver 50 ml in 250, right?
Mm-hmm.
This is 250 ml beaker. I have my puree. I have my puree here, and I'm delivering 50 ml of what? Of concentrated solution.
Mm-hmm.
Yeah, so 50 ml of con solution, and then you develop, or you dilute using the acetic acid acetate solution, and you adjust the pH, and you have your working solution, which you don't know M2 in this case. There is no way we can calculate M2, right?
Mm-hmm.
So at this point, you want to, using trial and error, which I assume that is what you did, is you deliver different volume of your working solution here from the period A or B, such that it gives you observance values in the midpoint. This is where you are targeting right here. Like, let's just put it somewhere there. Can you see that?
Mm-hmm.
You want observance values around the midpoint of this straight line. Just by eyeballing 0.2 to from 0.2 to 0.1, let's say 8, I'll say maybe around 0.5, maybe yours is around 0.6, I don't know the midpoint, right? Of the observance values, not the volume, but you are going with the observance values, like what is along the line, what is the midpoint? And you cannot use the volume you use and say that this is the molarity. We don't know the concentration. We just based on what? On the observance value here, that what is the almost the midpoint of this, so that we use trial and error here. You develop it, you analyze and say, oh, am I really getting the midpoint of these observance values? If assuming that, let's say 10 ml of your unknown, right? You have fine-tuned to 10 ml of your unknown solution, and it's giving you, let's say, 0.6, let's say 0.689 APS. This is observance values, right? APS. I see this is giving me almost like the midpoint of my, not the molarity, just the observance values here. So next time I will go with 9, because the observance will be, this will be sample number 1 now. For trial 1, and then you record its observance values. For sample number 2, 9 ml, this is sample number 2. Sample number 3, I'll say maybe 10.5, with just varying different volume, it will be 11. You see what I'm doing, right? This is 10.5, that's 10.5, and it's gonna be my sample number 3 here. Number 3, and then let me just push this up. And then here is sample number 4. I can make it 11 ml of my unknown. You see what I'm doing, right? And until you see the main, the whole idea here is to have different volume. We can give you 5, all right? We can give you 5 samples, sample 1, sample 2, sample 3, based on the midpoint on your calibration curve. And each time you are collecting the what? The observance values. All right? Now, I will pick one data here and show you from here, there is a worked example on how you can determine the mass percent in sample number 1. Can you see right now? Can you see my my screen?
No, I still see the writing.
The writing, right?
Yeah.
You see here if it's going to, I thought it was, I thought I shared my screen. Right. Can you see the screen now or no? You can see the screen now?
Yes. Yeah, I
so
can see
now, I wanted to share a document here. Can you see now?
Yeah.
So here is an example on how to determine the mass percent of iron in a sample. In one sample, in trial 1, assuming you had massed out 0.092 grams of your unknown, you went ahead and here you determine the you prepare the solution in 1,000 ml, and then this is the concentrated solution. You once you have your concentrated solution, here is the working solution. Still, we don't know molarity 1, molarity 2. Remember, this will be concentration here is molarity 1, concentration here is molarity 2. We're still tagging it the way we call it in the standard. M1 is for the 1,000 ml flask. M2 is for 250 ml flask. You see how you keep track of M1, M2, right? And then now once you have now the M3, this is what happened. You deliver the one you had 10, 20, 40, whatever, the 5, or, the 5, not the one for the standard, for your unknown, the volume, right? Which went into what? 100 ml volumetric flask. The concentration for iron in your unknown, we call it M3. So there is M1, which we don't know. There is M2, which we don't know. And then there is M3, which we will figure it out using the slope of your calibration curve, which is the molar absorptivity value for iron, and the observance for that sample. So if you did that, this is what will happen. That suppose your observance value is 0.0722, right? How do I find M3? In order to find the mass percent, you have to work your way back to M1, and then you convert M1 to number of moles, and then you convert the number of moles to grams of iron using the molar mass. And this is how you go. Start with M3, that what was the observance for that particular sample? Using the slope, I'm assuming that this was the slope. You have your own value. And then this is the y-intercept from the trend line. You can either have positive or negative. You know how to rearrange, right?
Yeah.
And this will give you what? This will give you your M3. So the next step is to find M2. You're going to follow this example. It's worked online, and you should have a handout for this document I gave you, right?
Yeah, I have that document.
Yeah, so after getting M3 from the observance values, you now use dilution law, but you are now labeling it as M2V2, M3V3, so that you use the information you have for M3 to find the molarity 2, which V2 is what was the volume you use in your sample number 2 in the unknown. That is your, and then M3 is the molarity you will get here, and all solution were diluted to 100 ml. So it's going to be constant. But this value you see here, 40 here, it will vary from sample to sample to sample. Because you have to, to get 5 samples, you have to change just around the midpoint. So maybe next time it will be 42, 41, because it's just going to be around there to get the 5 samples. So we have M2 here. The next course of action is to find M1 using dilution law, M1, V1, M2, V2. This is the, remember, you don't take your mind to 1,000 ml volumetric flask. Remember, to make solution 2, which was in 250 ml, you use 50 ml of V1. But M1 is what we are looking. V1 is 50 because you delivered 50 of your working, concentrated solution to make the working solution. You didn't use the entire 1,000 ml. Because you may think that, okay, in the iron wire, I was using the entire 1,000 ml to find the concentration. No, we don't know M1 at this point. That's why we are using 50 ml. And 250 ml here is for solution 2, the working solution. And at this time, we have molarity 2 from here inside that. Make sense?
Yeah, that makes sense.
And then once you have your M1 now, this tells you these are the number of moles of iron in the concentrated solution. The entire 1,000 ml, you know the concentration, you know the number of moles. From the number of moles, molarity times, volume in liters, if you know, it's the same thing as it was in liters. You see, this is molarity, because it was in ml. And then you convert to what? You convert to mass using the molar mass of iron. And that will give you the mass. And from your original mass, that is what you started off with in the dissolving in 6 molar HCl. diluting to 1,000 ml flask, the original mass of your unknown. I use 0.02, 0.0929 as an example to show you how you can find the mass percent of sample number one. You do the same thing for sample number two because they will not have the same observant values. And then you work your way.
Okay.
Does that make sense?
Yeah, that makes sense. That helped a lot.
It helps a lot. And that's why I say, let me just ask for your permission to record, and then I'll share with the, with the rest of the classmates to see if they will help. Maybe somebody is struggling right now, and this information may help them.
Yeah,
Is
that's
there any
fine.
question?
No, I think that's about it.
All right, thank you. Good luck. I extended the due date until tomorrow. You saw it, right?
I saw, yeah. I should
Yeah.
be able to get it in within the next hour though. I was just a little
Okay,
confused
because
on
you now
calculations.
you have the information, everything in there.
Yeah.
Okay. Thank you. Have a good day.
You too.
Bye.